Okay, dear guests, dear online visitors, we are starting our next session, which is devoted to artificial intelligence and computer vision, mostly computer vision, but there will be some surprises for text analysis. And we start our session with Mohamed Ahmed, who will present on, he will say what he will present. Yeah, if you have 20 minutes, please start.
Hello. We will talk about fusion of Today we are going to talk about fusion of data from LiDAR and camera for self-driving cars. My name is Mohamed Ahmed, and me is Professor Alexandr Klimchik and Dr. Riby. So let's start. Our table of content is as following. We will go from introduction until we reach our conclusion. So let's start with introduction. So here is a typical data from self-driving cars. As we can see, the up is the image from self-driving cars, and down is a point cloud. So let's talk about first the images. As we know that a colored image is composed of 3 channels, red, green, and blue, and each channel is a number from 0 to 255. But what about LiDAR? What is the other data? The other data is composed of points, and these points have 4 values. As some of you already guessed, the first 3 values are x, y, and z of each point, which is the coordinates of this point, and the 4th value is the intensity of this point. So let's talk more on LiDAR. The LiDAR is, we can imagine it as a laser beam that only fire the laser and wait it to return. And it records the time of flight, and then from it can get for us the distance. So a typical LiDAR will have 4,500 rotation step. So for the 360 degree, which make it like for resolution 0.08 degree. And for each LiDAR, it have like fired vertical arrays. So, for example, in our LiDAR, it have 48 vertical fired laser beams. For other LiDARs, it can be 32. Other types, it can be 16. So let's multiply this 4,500 rotation multiply the 48 vertical laser beam. That gave us for each 360 rotation, which we call frame. It can give us up to 216,000 points. And the LiDAR can reach up to 250 meters in best cases. And actually it can reach more than this, but it would require more power, and this can make it dangerous to the human eye. So like in most cases, it will be 150, about 150 most. For LiDAR camera, for each sensor, it has its own strengths and its own weakness. So what we are trying to do, we are trying to take the best from each one and make the fusion so we can make our models better. So for example, for a LiDAR, it can be bad in like raining weather. Camera can be better than LiDAR. And for example, for a foggy weather, camera could be bad and LiDAR could be better than camera. Our dataset is the Kitty dataset. It's a famous dataset that contains data from self-driving cars. And then after we trained our model on the Kitty dataset, we verified it on our own data, which we used in it Velodyne 32 and the USB camera. That was our hardware. So let's go with the problem statement. So first problem that we face with the LiDAR is that the LiDAR is sparse. So how the LiDAR is sparse? The LiDAR, as we said before, it could reach to 216,000 points per frame, but actually not all of these points return back. So it's about maybe half of these points return, which make it about 120,000 points. So imagine that for a front camera only. That would make it like a 90 degree, and then we will cut this 120,000 point into 4, then that make it 30,000 points. So for front view points of a LiDAR, that would make it 30,000 points. So why we say it's sparse? Imagine an image that have 1,000 times 400 pixels, that would make it for 400,000 pixels. And if we project these 30,000 points from LiDAR to the image, then not every pixel will have a deep information. That's why we are saying that the LiDAR is sparse. The real problem is that if we will deal with the point cloud data, that the performance will drop significant if we want like a high resolution or a high accuracy. So what we need to do is that we need to make our model good enough and work in a real-time manner. That we are trying to achieve, because it's a trade-off. We can make a very good model, but it can't work in a real time. So that's what we are trying to achieve, that we want to make a good model as possible and to make it work in a real-time manner. So the methodology we use here. So let's talk first about the types of fusion. So we have 3 types of fusion: late fusion, early fusion, and intermediate fusion. So for the late fusion, it takes the data from the camera, for example, and pass it through a model and give you an output, and then it takes the LiDAR data and pass through a model, separate model, and give you output, and then you make the fusion after both models give you the output. And this is good for keep independent strength of each sensor. So for early fusion, we pass both of the data to a model that can take data from both camera and LiDAR, and the model gives you the output at the end. And for intermediate fusion, that's we pass camera and LiDAR through and mix them through different models from the beginning, and even at intermediate phase, we take the feature extracted from these models and we pass it to another models. And for intermediate fusion, that make it very slow, and probably it's not much used for fusing data for different sensors. What is used is late fusion and early fusion. So what we are going to use, we are going to use the late fusion here. So why late fusion? We use late fusion because we can use the pure feature from each model separately. So here is a LiDAR. The LiDAR can give us like a point cloud, and then we pass it to a 3D object detector. It's called complex YOLO, and this complex YOLO can give us like a 3D bounding box. And for the camera, it gives us the image, and we pass it through YOLO V3, and this gives us a 2D bounding box. And then we make the fusion, and then it gives us like the final results. So this is a typical YOLO V3, that the 2D model that deal with the camera. But let's talk more on the 3D model. What is complex YOLO? The complex YOLO, it uses YOLO as we can see, but it's complex because it uses a pre-processing and a post-processing step. So what we are doing, or how we are using YOLO with the point cloud data. Firstly, as we can see that the point cloud data, we transform it to an RGB image, and then this RGB image, we pass it to YOLO. And after we pass it to YOLO, and after it detects the objects, then we use an Euler region proposal network. And so it can give like the bounding boxes detected a rotation. So we can detect our objects in a rotated manner. So let's talk more on this RGB map. What is this RGB map? So imagine that we have our point cloud. So we look it from a bird's eye view. It's like from a top view. And then it will have a 3-channel. We try to transform this point cloud to a 3-channel, red and green and blue channel. So what is the red channel detect? The red channel is the more intensity the point have, the more red it will be. For the green channel, the more high the point is, after normalization for sure. But the more high the point is, the more green it will have. For the blue channel, the more density, number of points are together, then the more blue it will have. Then we mix all of this together, and as you can see, some of the object can appear if they have like for one object it will have maybe same height for some points, same intensity. So that make it clear for the RGB map. And then we pass it to the YOLO. And after it gives us like the bounding boxes, we can pass it through Euler region proposal network. So after this, that's what we do so far. Here, after we take the output from both models, the complex YOLO and the YOLO V3, we just project the 3D point cloud bounding box. We project it to the image, and we compare both the 2D bounding box with the projected 3D bounding box. And we see if even if they have even if both models have a low probability of detection, but they have detected the same object, then we approve this object. If not, even if one of them detected but with a high probability, then we will approve this object. So let's go to evaluation and discussion. So let's talk more for evaluation and discussion. We use precision and recall. So let's talk more about precision and recall. What is precision and recall? The precision is true positive over true positive plus false positive, and the recall is true positive over true positive plus false negative. So let's imagine that what is happening here. Let's talk more in precision and recall. So imagine that our model is able to detect. Imagine that we have 10 objects in our frame. If our model could detect 2 objects correctly from this frame, then we can say that our model didn't miss any objects, didn't miss or didn't detect something wrong. But it's still a very low recall. So it have a 100% precision, but its recall is 20% because it's only detected 2 correctly out of 10. But imagine that our model is can detect everything, but it can give other bounding boxes that is not correct. Then we say that it have a very high recall, but a low precision. So what we are trying to do is that we are trying to find an intermediate trade-off between them. That's where we came to the precision and recall curve. So here is a typical precision recall for 3 classes. Our 3 classes are cars, cyclists, and pedestrian. The cars are in red, the cyclists are in blue, and the pedestrian are in green. So here is the precision recall curve for the complex YOLO alone. And as we can see, for a very high threshold, it have a very high precision, but a low recall. And for a very low threshold, it have a very high recall, but a very low precision. And that's the precision recall curve for the 2D detector, the object detector YOLO V3, and here is the precision recall curve from the fusion. But let's mix all of the 3 together and see what happening. So here is the precision recall curve for all the 3. So for the solid lines is fusion, and the dashed line is from this 3D complex YOLO 3D for the 3D LiDAR data, and for the dotted or faded line is from the 2D data. So as we can see, for example, let's take the red lines. As we can see, the fusion could enhance more the precision and recall for the cars, and even for the other classes, it could enhance. So this is our results for the table. For example, for the complex YOLO alone, it was 96%. For the YOLO V3, it was 78%, 78.5%. And the fusion managed to enhance this by almost 1%. For the cyclist, it's enhanced it by almost 2%. And for the pedestrian, it enhanced the average precision by almost 4%. And the average precision for all the classes together, it was enhanced by almost 3%. But as consequences, the frames per second were dropped from 50, for example, to 28. Because we were using serial like we're using each model like in a serial way after each one, and this could be handled by parallelization. So result and visualization. So this is the results on our Kitty dataset. So for the green boxes, it's the detected boxes from the 2D YOLO 2D object detector model YOLO v3, and the other colors is from the 3D object detector complex YOLO model. As we can see, some objects could be detected from both models, and some objects could be detected only from one model. And this is a bird's eye view on our point cloud, as you can see. So let's take some case. This case, for example, it couldn't be detected by LiDAR. It couldn't be detected by the complex YOLO, but it could be detected by only the camera. As you can see here, the LiDAR couldn't detect anything here. That's why we are trying to use fusion to take the best from each sensor. So in some cases, when one fails, the other can support, and in some cases, both can support. So let's go to some visualization here. Here I started to use our models for real data. So let's first start with this. This is some data that I downloaded from the internet. And as you can see, it's a car moving in the street, and it starts to detect some objects, cars, pedestrian, and cyclist. And this I was trying with the LiDAR and camera in the library. So I was trying to move in front of the camera. As you can see here, before I enter the frame, there were detected a wrong object, but it couldn't appear here in the point cloud because, and it couldn't give it any distance because this object was wrongly detected. But when I will start to move, I was detected by the camera and by the point cloud model, and I was detected here on the point cloud as well, and it was gave me coordinates for my position, the dimensions and the centroid. So that's if our model like detects some wrong object, and the 3D model didn't detect this, then probably, and it have a low probability, then it will be removed. But if an object detected, even if it have a low probability, but detected also by the 3D model of the LiDAR, then it will be validated. And here it was in the garage. Because there were some trucks don't validate on, and that was me. So that's how we validated our work. So that's what I just explained. For me, it was a true positive detection, and it was detected by the LiDAR. So the fusion output could give us some results, but when some positive objects detected, then it can't give it any validated data. So for the conclusion, image-based fusion combines information to obtain better results than the 2D object detection model and 3D object detection models separately. However, the processing speed decreased, but as we said before, we can improve this by parallel processing, and that's what I did after this. The proposed methods have been implemented on the Kitty dataset as well as our custom generated dataset from the Buildline 16. The result, Buildline 32, sorry. The results show that the proposed method enhance the result of individual method that use point cloud and image data. So for future work, I will continue work with Kalman filter approach, and then I will continue with parallel processing, and probably later I will use the early fusion in my PhD. So contribution is that our proposed image-based fusion approach managed to enhance performance by 1% for cars class, 2% for cycles class, and about 4% or 5% for pedestrian class. The average precision for all classes was enhanced by almost 3%. So thank you for listening, and I'm ready for any questions.
Thank you very much. I just want to ask you sometimes look at me because I'm sure the timing, we don't keep the time, but you already spent all the time for your presentation without the questions. So any questions online? Any questions offline? Mine first? No, offline, guys?
I have a question.
Okay, please go ahead.
Can you hear me?
Yes, yes, I can.
Okay, so my first question is, what about the frequencies of the lidar and the camera input information?
Sorry again.
Frequency of the lidar and the camera.
Yes, frequency of the lidar is about 10 frames per second, and for camera is 30 frames per second. But we drop it to 10 frames per second because we don't need the excess information.
Okay.
And
so this object detection, it's performed for scan to scan, right? For only points which are in one scan.
For what? Sorry again.
The object detections is performed only for one scan. You don't fuse point clouds from many scans.
Yes, we didn't do tracking yet.
Okay. And what about the transformation between lidar and the camera frames? How do you calculate it?
Yes, for the kit dataset, they give already transformation matrices between the lidar and camera. For our custom generated data, we make a calibration between the camera and the lidar to ensure that for what the point cloud for the object that is seen by the point cloud is exactly transformed to the image in the same correct frame.
Okay, and last question is: do you take into account the distortion of the points in one scan due to the motion of the lidar?
There were actually, I didn't see any distortion between scans. I believe that the lidar drivers is handling this internally, so there were any distortion that I see. I know what you mean, that for high speed that maybe the point cloud will be missed, but I believe that the lidar is handling this internally.
Okay, thank you very much, Mohamed.
Thank you.
Thank you for your questions. Unfortunately, we are short on time, so thank you very much for the presentation. The next speaker is Tagir Muslimov, right? From Ufa State Aviation Technical University.
This one? Yeah.
Hello, everyone. My name is Tagir Muslimov. I am a senior researcher at Ufa State Aviation Technical University. I think I'm not really in the right section because I'm currently more involved in control theory, not in computer vision. It's okay. So First of all, I would like to talk about what our small research group does. We are currently working on a joint scientific project with Korea Aerospace University from South Korea. This project is about decentralized control of unmanned aerial vehicles formations. And what we are doing now, decentralized, robust, adaptive formation control of UAVs, fault-tolerant formation control, autonomous collision avoidance for UAVs, and trajectory optimization for UAV formations. So we have chosen path following over trajectory tracking for several reasons. Most importantly, this method is more suitable for fixed-wing UAVs. This is because this type of UAVs have limited maneuverability, and this method is more suitable for some tasks such as tracking and moving objects. The essence of path following is the asymptotic pursuit of the UAV to a given limit set, which is called a path. So there are existing solutions for path following method. We investigated the well-known vector field method. The idea is to define a vector field at each point in the UAV flight space. This vector field specifies a desired track angle at every point. However, this method was developed for a single UAV, and it cannot be directly applied to formations. Therefore, we have modified this method for formations. So we choose the following model to implement decentralized interaction in UAV formation. In this model, each UAV interacts only with its neighbors. Thus, the control algorithm for each UAV are formed based on local information only. So this control can be considered decentralized. We propose such control laws for the UAV formation. The peculiarity of these control laws is that they directly take into account the limitations on the input control signals for the autopilots. And we proved the global asymptotic stability of the UAV formation system using the control laws from the previous slide. We did this using Lyapunov method, Lyapunov functions method. This result was published in our journal article, and control algorithms can be derived from these control laws. During flight, the dynamics of the autopilot UAV system can change. Therefore, we developed adaptation algorithms based on the adaptive backstepping method. These algorithms make it possible to maintain the stability of the flight of the formation system, even when the dynamics are unknown in advance. So this slide shows the work of adaptation algorithm. As you can see on the left of the slide, the UAV formation system loses stability if the parameters of the control algorithm are incorrectly chosen. This wrong choice is inevitable when the dynamics of UAV change during the flight. On the right side, it is shown that the stability was preserved due to operation of adaptation algorithm. Okay, so for this formation of UAVs, the question also arises: what happens if one or more UAVs are lost? As we were able to find out, there is no loss of stability because the system finds a new equilibrium position. In this situation, there is an increase in the interaction between the UAVs. Therefore, the final cruising speed of the formation increases. And we have developed a special adaptation algorithm that eliminates this effect by adjusting the new equilibrium position. To avoid collisions in the formation, we investigated an algorithm based on a modification of the standard finite state machine of flight altitude control. We added an overall control loop and an adaptation algorithm based on control with the reference model. The asymptotic stability of the adaptation loop was proved using fuzzy Lyapunov functions. The negative definiteness of the Lyapunov function derivative is provided by choosing fuzzy rules. And the interesting thing here is what happens if y with dot equals 0. In order to derivative to remain negative definite, we have to require that the sum of y and v also equals 0. Turning to the topic of the paper, we used microdrone with an open source software for indoor testing. This model has special expansion boards that allow us to navigate indoors. There is a board for measuring distances in 4 directions, around and overhead up to 4 meters, and separate boards for measuring from below and estimating the distance traveled based on Kalman filter. We wanted to test collision avoidance without using a global navigation system. So we developed a simple algorithm, the essence of which is that when an obstacle is detected, the drone starts moving sideways until it loses the beam. Then a certain distance reserve is taken and it continues its movement. On the right side is shown the trajectory of the bypass. This slide shows measurement of distances around the microdrone as well as estimates of angular positions. Overall, the algorithm proved to work, but due to drift of the estimates in Kalman filtering, the accuracy is lost as we move. Also, the distance measurement board itself is not particularly handy for more sophisticated obstacle avoidance algorithms. So in the future, we also plan to use a global navigation system based on virtual reality base stations. So thank you for your attention.
Okay, thank you very much for your speech. Any questions online? There's a question offline as well. Please hold the mic.
Can you please explain what is the definition of stability for this system? Как вы определяете устойчивость для системы?
Для системы информации имеете в виду?
Ну, для вот этой системы дрона. Вы говорили, что про устойчивость по Липунову, я просто пытаюсь понять в каком смысле, что сводится к нулю в итоге.
Если говорим о устойчивости по Липунову, там у нас задаются состояния, то есть, допустим, это может быть расстояние между дронами, и то есть мы должны обеспечить устойчивость по Липунову, то есть асимптотическую, то есть это сходимость к заданным положениям. И плюс
ошибка относительно траектории должна к нулю стремиться.
Да, то есть это будет ошибка между ними и ошибка, может быть, допустим, до вот этой заданной линии.
Понял. Скажите, I'm sorry for asking introduction. So what is, how did you prove this stability? Like, did you use linearized model? Как вы устойчивость?
Yeah. So we used Lyapunov functions method.
Non-linear.
Yeah, non-linear version of. So we have a non-linear version of our system equations as a differential equations, and we can use Lyapunov function method.
Your UAVs, if I understand correctly, they are described by Euler, normal Euler equations. So you have like 6 equations of motion. I don't know which model you used, but do you mean you derived Lyapunov function for those It will be 12 state variables.
Yeah. No, we consider separately the autopilot stabilization, which can be seen as linear system analysis, and trajectory stabilization. In this case, we have to use nonlinear equations because the distances can be very large, and we should take into account the restrictions on input signals.
So what was the dimension of the nonlinear Lyapunov function?
It depends on the number of UVs. So, for example, we have like n UVs. I think it would be 2n because.
Yeah, I understand. But isn't it a very large number of equations? How do you find such a Lyapunov function?
No, that as I said in the beginning, because we use decentralized version of interaction. Each UV interacts only with neighbors.
And that is sufficient to prove stability for the global system?
Yeah, it's quite complex.
It doesn't follow from Lyapunov function method. So Lyapunov function method has to be one Lyapunov function. So everything. If you use decentralized arguments, there is additional analytical steps.
No. It only be like many sums, logarithms. We should sum up several like summands and.
Okay, so you have basically the same Lyapunov function for each UV. You just sum.
Yeah, but the problem is they interconnected, and that's why it can be very complex proof of stability. But we managed to do it. Yeah.
Sorry for some questions.
Thank you.
Okay, thank you. Any questions about Victoria? Thank you. I think we're again back on track. Thank you very much, Tagir, for your presentation. And yeah, and the next speakers are online. They represent Bauman, Moscow State Technical University. If they will online, please. Yourself. Ahmad Ali. Can you hear us?
Yes, hello. Can you see my presentation?
Yeah, can you make it full screen?
Of course. That's good.
Yes. Yeah.
So, so you can start. Please go ahead.
Okay. Hello, everyone. I'm Ahmad Ali Deeb. I'm a second-year PhD student at the Faculty of Computer Science, Artificial Intelligence, and Control Systems at Bauman University. I'm going to present a paper handles object detection approaches that can be used in robot navigation. Object detection is an algorithm related to computer vision and image processing that deals with detecting instances of semantic objects of a certain class, such as humans, building, or cars, digital images, and videos. Object detection has attracted significant attention for autonomous robots to its notable benefits. It can be used in autonomous vehicles for the development, guidance systems, pedestrian detection, dynamic vehicle, and obstacle detection. Most of the time, the robot system cannot be equipped with heavy devices due to the weight and power consumption. Therefore, embedded systems play a vital role for object detection. So in this study, we compared various object detection algorithms and different embedded systems to execute those algorithms. And based on the comparison, we choose the best algorithm with the best embedded system for object detection in a robot system in real time. Object detection algorithms that we had explored in our work can be divided into two approaches. The region proposal-based framework, such as RCNN and its variants, is a two-stage process, matches the attentional mechanism of a human brain to some extent, which gives a coarse scan. You can hear me, right?
Yes, continue, please. Continue.
Which gives a coarse scan of the whole scenario firstly, and then focuses on regions of interest. Two-stage networks can achieve very accurate object detection results. However, they are typically slower than single-stage networks. Regression classification-based are single-stage frameworks based on global regression classification, mapping straightly from image pixels to bounding box coordinates and class probabilities. An example of these frameworks is YOLO algorithms, which they can reduce time expense. Single-stage networks can be much faster than two-stage networks, but they may not reach the same level of accuracy, especially for scenes containing small objects. RCNN, or region with CNN, one of the first breakthrough of the use of CNNs in an object detection systems that had a much higher object detection performance than other popular methods at that time. It still takes a huge amount of time to train the network, as it would have to classify 2,000 region proposals per image. RCNN model took a huge amount of time to train the network. Faster object detection algorithm known as fast RCNN had been built to circumvent this problem. Instead of starting with the regions proposal module and then using the feature extraction module like RCNN, fast RCNN proposes that we apply the CNN feature extractor first to the entire input image and then propose regions. Faster RCNN is the third iteration of the RCNN family, developed in 2016. Similar to fast RCNN, the image is provided as an input to convolutional network that provides a convolutional feature map. But instead of using a selective search algorithm on the feature map to identify the region proposals, a region proposal network is used to predict the region proposals as part of the training process. On the other hand, mask RCNN is an extended version of faster RCNN for pixel level segmentation. Mask RCNN work by adding a branch for predicting segmentation masks on each region of interest, in parallel with the existing branch for classification and bounding box regression. The branch is fully convolutional network on top of a CNN-based feature map. Once these masks are generated, mask RCNN concatenate them with the classification and bounding boxes that result from faster RCNN. Overall, it generates precise segmentation. YOLO used an innovative strategy to resolve object detection as a regression problem. It detects bounding box coordinates and class probabilities directly from the image. YOLO used some squared error between the prediction and the ground truth to calculate loss. The loss function composes of the classification loss, the localization loss, and the confidence loss. Since YOLO version 1 suffers from localization errors and low recall predictions, the YOLO version 2 shows a lot of improvement to increase the speed and accuracy, such as patch normalization, classifying on high-resolution inputs, convolutional with anchor boxes, and multi-scale training. YOLO version 3 is an improved version of YOLO version 2. YOLO version 3 can give multi-label classification to adapt to more complex dataset containing many overlapping labels. Tiny YOLO version 3 is a lightweight target detection algorithm applied to embedded platform based on YOLO version 3. Therefore, the running speed is significantly increased, but detection accuracy is reduced. Since we are dealing with robots that may be small in size, then we should search for embedded systems that are compact in size, low power consuming, and the most important feature is to have high computational performance. NVIDIA Jetson devices are embedded AI computing platforms that provide high performance, low power computing support for deep learning and computer vision. We can see in the table a basic comparison between different Jetson modules. Since Jetson Xavier embedded system is the most powerful among all other candidates, we will use it to benchmark different object detection algorithms to choose the most suitable for our task. We compared various object detection methods on two benchmark datasets, including Pascal VOC 2007 and Microsoft Coco. The dataset statistics are shown in the table. In Coco dataset, there are a lot of less iconic objects with a broad range of scales and stricter requirement on object localization. So this dataset is more challenging than Pascal 2007. In this slide, we can see an accuracy comparison between different approaches on VOC 2007. We can see that YOLO version 1 obtains a very poor result on VOC 2007 because it is not good in producing object localization of high intersection over union. Here, the figure shows the accuracy comparison results based on Coco dataset. Overall, region proposal-based methods such as faster RCNN and mask RCNN perform better than regression classification-based approaches like YOLO, due to the fact that quite a lot of localization errors are produced by regression classification-based approaches. We can notice that the results on COCO dataset are much worse than of VOC 2007. And this is due to the existence of a large number of non-standard small objects. The processing speed variation experiment was performed for each of the models on 3 devices. First, the experiments were performed on Jetson TX1, Jetson TX2, and Jetson Xavier that was released for edge computing. The performance results are in the form of a frame per second, are shown in the table. This table provides a quantitative comparison between different types of onboard embedded GPU systems. Using this table, one can choose the best algorithm and system for a specific operation. Regression-based models can usually be processed in real time at the cost of a drop in accuracy compared with region proposal-based methods. Here, figure shows performance of different object detection algorithms in terms of speed and accuracy. It is difficult to define a fair feature of different object detectors. Each case of real life can have different solutions to reach a decision concerning the accuracy and speed. Since the main focus of this work was an object detection for all robot navigation, we first need to figure out which algorithm provides faster and more accurate results. Here, the figure shows the performance in terms of speed versus accuracy trade-off for some object detection algorithms that are applicable on NVIDIA Jetson Xavier. Even though that YOLO version 3 Tiny is the only algorithm that can be implemented on Jetson Xavier in real time it is more than 30 frames per second, but our choice is to use YOLO version 2 on robot applications that demands real-time processing. The YOLO version 2 selection was based on its speed performance that is very close to real time and its accuracy, which is 40% better than YOLO version 3 Tiny. In summary, in this work, we have reviewed some object detection algorithms, including region proposal approaches like RCNN family and regression classification approaches like YOLO versions. We have also discussed the properties of some onboard embedded GPU systems that can be used to perform deep learning processing and the difference between them. In addition, we performed an experimental comparison on the performance of each algorithm in terms of accuracy based on 2 datasets, Microsoft COCO and Pascal VOC 2007, and in terms of processing speed by onboard embedded GPU systems. This paper can be used to determine the appropriate object detection algorithm for a specific task relying on speed accuracy trade-off. For future work, we are planning to do a comparison using more advanced algorithms, object detection algorithms, to make a comparison based on different datasets such as stereo vision, point cloud, or depth map for object detection, and make a comparison based on embedded systems power consumption. Thanks for listening, and I'm happy to answer your questions.
Thank you very much for your speech. Any questions from online? Yes. Offline. If you don't mind, I have a question.
Okay.
So you don't see me, but I definitely a real person. You said that the target of your research, the application, is to utilize these algorithms in embedded systems in robot navigation.
Yes.
Yeah. So, and I know that it comes from the name that these models, they basically use different amount of the number of parameters for inference. So, and tiny means that the model takes less memory.
Yes.
And so there are like 2 consequent questions. So first one, do all these algorithms which you run utilize GPU on your embedded systems? And the second, if they utilize or if they have the same equal opportunities, which one of them consume most power? So are they the same in terms of power consumption?
Yes, I understand your question. I'll start by answering the second question. About power consumption, actually, I said it is for future work, so I didn't do a power consumption, but it is really a good idea to do, and it is important to do power consumption on embedded systems. But I didn't do it, actually. For the first question, it is a lot, as you said, there is a lot of parameters that depend for inference. For example, the image dimensions and other parameters. So not all the algorithms, like for example, mask RCNN on embedded systems, it is very difficult to be applicable on embedded systems. But maybe if we make the image very small, maybe it will can give us some results. But I include it in the comparison because it is its accuracy is very high in comparison to other algorithms. So it depends on the situation, on the task, so that we can choose which algorithm we want to perform. But in embedded systems, actually, all RCNN family, it is very difficult to perform on embedded systems. I hope that I answer your question.
Just a small clarification regarding the algorithms which you could run on the embedded system. As I understand, all the systems, they do have the GPU. So did they all utilize this GPU?
I don't understand what you do mean by utilize GPU, not embedded system.
You can run a convolutional network on the CPU without any problem. So do they use the graphical card side?
On CPU, you can run it on inference, but for training, of course, it is very hard.
Definitely, but you use it for exactly for inference.
For inference, yes, you can run it on CPU. But it depends on the algorithm. Maybe some algorithms will be very slow.
I want to show that the main idea behind my question. The question is, for now, you have these parameters, these numbers of FPS, and maybe you'll study the power consumption. And what about scalability of your algorithm? So imagine like in 2 years or 3 years, the new hardware will appear. So how significantly will the performance change? So if the graphical card will do 4 times better computations,
understand your question. Actually, not only embedded systems are developing, but also algorithms are developing. So maybe in some few years, some algorithms will be much faster and need less power, less performance from embedded systems to perform. So in the future work, I can't decide what will be. So it depends on what I have in future. But of course, if embedded systems will be better than of those, so the results will be better.
Okay, thank you. Any other questions from the auditory, from the online? No. Thank you very much for your talk. And I think we can move to the next speaker, right? Yeah, and the next presenter is Karam. Yeah. You're fine.
Okay. Hello, everyone. My name is Karam Almaghout, PhD student here in Minneapolis University. And today I'm going to present our recent work entitled Vision-Based Two-Robot Frameworks for Deforming Flexible Linear Objects. So, the outlines of this presentation would be, we will start with brief introduction and the preliminaries. Then we will I will introduce the approaches used in our method. Then we will discuss the experiment and ending up with conclusion and our future work. So when we mean what we mean by deformable linear objects are objects like cables, ropes, wires, and etc. The manipulation of these objects can be categorized in 2 main sets. The first set is the assembly, like knotting and insertion, while the other one is shape control, which means deforming the DLO, the object, from a configuration into another one. This task can be handled either by contact-based, using contact-based with the environment, or without. In our research, we are considering the shape control with no contact. So this is a glance of our proposed framework. We have two robots, a camera, and we have the cable fixed to the robots in the vectors, and we are trying to deform this cable from one shape to another one, while the desired shape is passed through the controller. So in order to do that, we first have to find a good, like a practical representation of the cable. So we model the cable as a multi-link body, while in a brief, it's like a set of endpoints, and these points are connected with each other by rigid links. So we will refer to the rigid links by length by LS, and the number of points is N. Here we have P is the set of cable points, T is the set of the desired shape points, while R is the robot's configuration, X, Y, and Y. So the first step is how to model the cable as this set of points. So we assume that we consider that one of the robots has a marked tool with a specific mark as considered as the starting point. Then we detect the cable and extract the center line of the cable using thinning algorithms. Later, we use a circular mask. We place this circular mask at the starting point, and we check for the intersection between the cable center line and this mask. The intersection point would be the next feature point, and the mask will move forward to the next intersection point in order to figuring the next feature point. By sliding the mask along the cable, we will obtain the final result as like the cable is modeled as set of points. In this case, we have shifted we can redefine the shape control problem by manipulating the cable points towards the desired points, as we can see in this figure. And in order to do that, we have to map the motion. We have to find a model that maps between the motion of the cable points and the robot in the vectors, which is the Jacobian matrix between the robot and the cable points. So here we are introducing an approximate model based on two observations. The first observation is the diminishing rigidity property of the cable, which means it can be seen that from the figure above, the grasp point, the point at the top, is moving completely rigidly with the hand. While as far as we go far of the hand, the points are starting to act less rigid. The second observation is as much as the cable is stretched, is moving more rigidly. So as much as for the cable point PI, as much as D capital minus this monitor equals 0, tends to 0, the point PI tends to act as like it's rigidly connected to the robot are yes, it's that it tends to act more rigidly as this relation tends to 0. So use based on these two observations, we compute the Jacobian for the cable point Pi, and the robot M, since we have two robots, so M could be 1 or 2. Then this is the first, the Jacobian here is still rigid Jacobian, as like rigid links between Pi and Rn. Then we define the diminishing rigidity function as an exponential function, since based on the literature research. Then, since the cable point is being moved by two robots, the motion of this point is a ratio of each robot. So we define these two functions, mu and alpha. So we ended up with the Jacobian for Pi multiplied by alpha and mu, and for the Jacobian of Pi that undergoes the guidance of two robots can be given by this formula, and next we can obtain the required, if we consider that delta P is the difference between the cable points and the desired points, we can obtain delta R, which is the required motion from the robot by computing using this formula, and which is J here is the pseudo-inverse Jacobian. The third approach here is if we assume that the desired profile is part of the initial shape of the cable, so the motion could result some excessive forces, or the motion of the robot could exceed the cable length constant. So here we introduced an intermediate profile algorithm, which can, in another expression, can be considered the waypoints of each cable point. This method generates a cable profile that leads from the initial to the desired one as an intermediate profile, and these intermediate profiles all are are reachable from the robots and within the cable length constraint. So the hardware setup, we used two Poker robots and an RGB camera. The pipeline of the methods are written in C++, and for the computer vision in Python under the framework ROS. So this is the results of the virtual feature point algorithm. Here you can see the input frame and the extract detected cable and thinning the center line of the cable, and the starting point and the mask. We insert these three images into the virtual feature points algorithm, and we obtain the final result, as you can see. Here, there is another example, shows how the cable is sampled. The intermediate profile, here you can see, after we get the cable sample, we generate the desired profile based on the number of the cable points. And after that, we generate the intermediate points. Here you can see each intermediate point can be considered as a local desired profile that guides the cables towards the final desirable. The manipulation results. Here, the results of two experiments, and this is a video of experiment one. The average error was in range of 7 millimeter, and the maximum error was in range 9 to 10 millimeter. The manipulation result was here. The figures shows how the error is compared to 0, but compared to 4, 5. So the manipulation planning algorithm method was not able to accurately fit the desired shape due to some limitation, since we didn't consider some properties like stiffness or internal forces between the cable and the cable. So in this presentation, we have proposed 3 approaches: the virtual feature point approach, the intermediate, and the manipulation planning. The virtual feature point algorithm was reliable, showed a reliable performance, and in the manner of accuracy and speed, it was able to detect even if the cable at the edge of the image frame. However, it does not consider the occlusion or if part of the cable outside the camera frame. The intermediate profiles generated the profiles within the cable length constraint. We consider the step between each intermediate profile as the length of the segment, the length of the cable segment. In the future, maybe we can make this practically more accurate by using an adaptation or some online tuning. The manipulation planning model was able to guide the cable towards the desired shape. However, it was not able to finish the manipulation to make the cable accurately fit the desired shape. But the cable was always converged to its desired configuration and does not diverge. Future work improving the VFP algorithm to be more robust in different illumination conditions, and improve the manipulation planning to consider more cable properties in order to get better results, and exploiting force sensors to improve the manipulation performance and the cable length constraints. That was all. Thank you.
Thank you very much, Karam. Any questions online? Maybe there are offline questions, because I have some. I believe that I heard the part of this speech a couple of months ago. And my question is the following. So from your presentation, what I see, the examples which you provide, like the pictures and the videos, they're pretty simple. So the task is not very complicated. On the other hand, what I see that you still fail to meet the desired trajectory accurately. And from the numbers which I saw, like the error is approximately 7 millimeters, whereas I think it's comparable to the length of the sections.
Oh, it's 7 millimeter. Here it's 7 millimeter. 7 millimeter.
7 millimeters. Yes. Yeah, I mean the joints themselves are of a comparable size. So my question is that if you still on this simple setup fail to exactly reach the desired thing, maybe the problem is instability. Yeah, so I'm thinking, and I want to ask you the question. Maybe you did this experiment. So how the number of joints in your model influences the accuracy of the result?
Thank you for this question. Actually, I think like the number of joints in the cable should be considered according to the cable stiffness property. So, for example, if we have a thick cable and the diameter of the cable, because in such thick cable, big diameter, and high stiffness cable, the number of cable points can be reduced to the minimum, since we don't have this flexibility in our design. So yeah, it would affect the system, and vice versa. If I believe if we increase these points more than the cable, it's like degree of freedom, or its flexibility, we will stuck in it. We will not obtain the accurate results.
So your answer is if, because like my question was that did you try different, like for the same cable, you try it's accuracy around 10, what about 5,
Yes.
20? How the accuracy changes after this?
Yes, I actually tried with 20, 30, and 12. But actually, I couldn't say that I got like a clear difference between this point. I stuck with considering taking a percentage of the cable as a segment length and divide the cable by this segment length. So for example, I'm taking 10% of the total cable length as the segment length, and divide the cable. I didn't get significant difference between changing the points up to now.
So actually, my question was that what if you make it significantly smaller? But I see that with growth, yeah, definitely you will not have a significant improvement. Okay, maybe any other questions? No? Just from as I'm not a robotics professor, so I'm interested. So can you provide a couple of examples for me where I can use this technology in future?
Yes. Actually, first example is in industry, automotive industry, mainly for cable routing, wire routing, even not automotive, maybe for where there is a cable routing, we may need this. We will need this task also, and it's completely manual for now. Also, for some cases, not for cable, but for deformable objects, we need to bend. For some example, if we have a linear object, we need to bend it and keep it like bended. And for example, after that, we apply a heat treatment to fix the shape. So this is also another direction of implementation.
Okay. So I believe that in the second case, the stiffness will change because you heat it or something.
After we hit it, okay, it's done. The task is done. So the task is to be bended, for example.
Okay, so I mean that in your case, you consider that like the relaxed state of your cable is like a linear, but in the future, like if you bend something and you, for example, do like a union, then the bended form will be now the relaxed one. So when you try to achieve the another form, there should be a different set of equations to solve.
Sorry.
Imagine you have the curved something which is stiff and which is already relaxed. Yeah, so will your model work?
Equilibrium configuration.
Like a staple, you know, the staple is already bended, but it's relaxed. So if you try to bend it, it should keep it in a different form.
I'm not sure I got it, but let's, for example, say if we have a cable, a very thick cable, and need to be heat treated before while bending. So for such case, robots can achieve this, and like it would be more safer to achieve it by robots rather than by humans.
Okay, my question was different, but I think that we are out of time. So thank you very much for your speech. If there are any questions, no. Thank you very much, Karam.
Thank you.
the next speaker, I think, is online. We will have a little shift in the topic. The next speaker will present on the natural language processing. So maybe robotics students and robotics colleagues will benefit from the completely different area.
Hello?
Dinar, can you please switch on your camera?
Yep. But I think when I will start presentation, it's better to turn it off to have more stable connection. Can you hear me?
Yes, we can. Please share your presentation. If you have one.
Can you see it now? Okay.
Yeah, great.
Okay, good day, everyone. I'm Dinar Zaiakhov. The topic I would like to talk about is exploring dimension reduction techniques for text dataset visualization. Let me smoothly introduce you to the topic. We all know that an easier way to absorb knowledge is a graphical form rather than dense text. There are multiple ways to picture the data. Some are targeting to present big datasets all at once. Others are able to show the specifics of the high-dimensional data. The examples of the first ones might be scatter plots to show the relation between parameters, or box plots to demonstrate the spread of numerical data, or donut charts, which are used to illustrate numerical proportion. The instances of the latter are spectrograms, which visualize the spectrum of frequencies, or tables, which structure the data and present features evenly. The challenge occurs if data is high-dimensional and numerous at the same time. We can use maps if there is a need to focus on data points, or spectrograms if data features are important. But showing both is problematic. We aim to address two characteristics in our work at the same time, keeping the significant words and showing their relation with other ones. The following are our significant contribution. We compared dimension reduction strategies and picked the option that is best for text data visualization. We suggested a set of guidelines for determining the best parameters for various text dataset sizes. We investigated text vectorization strategies and selected the solution that optimally embeds relationships in metric vector space. And we released our discoveries as an open source software to the community. We explored dimension reduction techniques to use them for a clear and understandable way of text data visualization. Now let's talk about what we used for that and how it was done. The first library that was used in our work is Spicy. Spicy is an open source library for natural language processing in Python. We used a trained pipeline of the English language. In particular, the lemmatization component was used to fetch the standard form of the words. The second tool was Gensim. It is a free Python library for topic modeling. The tokenization utility provided by Gensim was used to split sentences into distinct words. One more NLP library that was useful is NLTK. We utilize its corpora of English words to filter out the tokens that are not in this corpus. We compared several word embedding models and used Encore Web SM and Encore Web MD from Spacy. Those are English models trained on web data of size small and middle correspondingly. We chose the medium-sized model, which consists of vectors of dimension 300, since a larger pipeline indicates more accuracy, and middle one, unlike the small, offers static word vectors, which we found to be more stable. These vectors are designed to map semantic meaning into numeric proximity. To display vectors of dimension 300, first we need to reduce the dimensionality. From the standpoint of textual data, several approaches to dimensionality reduction methods exist. They are divided into global and local ones. We are not focused on global low-dimensional approximation algorithms, since they are effective at detecting general trends in data and emphasizing outliers, but they fail to retain dense clusters and perform poorly in visualization of dedicated clusters. We want to maintain local communities and small distances. Thus, we used local approaches. We focus on two local techniques, TSNE and SOM. TSNE is unsupervised machine learning approach. It enables the visualization of high-dimensional data structure in 2 or 3 dimensions, retaining a lot of the original information, with findings shown in a simple scatter plot. TSNE finds a way to project data into a low-dimensional space so that clustering in the high-dimensional space is preserved. The basic ideas of how TSNE works are as follows. First, we are determining the similarity between all the points in high-dimensional space using normal distribution. Using normal distribution means close points will have high similarity and distance points will have low similarity. We end up with a matrix of similarities. Then we randomly project the data onto lower dimensional space. Then we calculate the matrix of similarities for new lower space, but with the use of t-distribution. Without this distribution, all clusters will clamp up around the center. Finally, the TSNE algorithm will move points step by step in a direction that makes the new similarity matrix more like the first one. The second technique is SOM. SOM is an unsupervised neural network with a coherent layer in its architecture. But unlike most other neural networks, self-organizing maps are trained on unlabeled data for clustering purposes. They are quite good at simplifying high-dimensional data into easy-to-visualize two-dimensional representation. Let's dive a bit deeper and see what are the key concepts. The target space is known as a map space, and it is made up of components known as neurons. So the SOM predefines the number of cells that our data can occupy. Number of cells equals the number of neurons, and also predefines the shape of the target space. Each neuron is associated with a set of weights for each input. These weights will determine where each neuron after the learning process will be located in the map space. The training process can be summarized in 5 steps, which are initializing the weights, then a repeated process of selecting an input, finding the winning neuron of it. We use the Euclidean distance for finding the winning neuron, updating the neuron weights, and so on. During the updating process, the algorithm changes not only the weights of the current neuron, but also the neurons at neighborhood. The neighborhood function, the sigma parameter, which is the spread of that function, and topology of the map space. Topology usually is rectangular or hexagon, as in our case. These all are participating at updating the weights. We compared the mini-SOM implementation of SOM and TSNE from sklearn. We focused on 2 things in particular. We discovered that even when using a fixed random seed, the TSNE algorithm is not stable in terms of the final picture. We didn't use these procedures since we feel our findings should be repeatable. Second, we evaluated the pictures produced using various initial dataset sizes. We concluded that the sparse results which we were receiving from the TSNE approach didn't satisfy our initial goals of having a map with certain borders for convenience. As the last step of deciding in favor of SOM, we looked at how dataset size and hyperparameters affect visualization time and quality. Even with thousands of data points, the TSNE algorithm is slow. We provide a background set that reflects the language in general for every visualization. This may be a general English language with most common terms, or particular language like Russian literature or quantum physics language. In our case, it is the COCA dataset. More precisely, nouns and verbs, which are 32,719 of them. The background set is utilized in the training of the dimensionality reduction model. In addition, there are none or numerous foreground sets that are linked to the background. Missing words or unique terms or subject clusters can be identified by comparing the foreground and background visually. For temporal analysis, stylistic matching, or the detection of restricted region-specific phrases, comparison among the foregrounds might be employed. Here's the illustration of the visualization. We can see the background, COCA dataset, the part of it, given with the hexagonal blue tiles, and the foreground set given with red hexagons. All of the above mentioned data are presented with a bokeh Python library, which is used for creating interactive visualization. Now let's see what results we got. We manually verified word distributions to measure clustering quality. After exhaustive grid parameter search, we chose sigma equal to 2, learning rate equal to 5, and number of iterations equal to 50,000 to form a good clustering on our COCA data. The cluster's quality in physics text might be seen in the figure. A comparison of one group of physical text to another is shown now in the slide. Please note that the map center has a huge cluster of shared vocabulary, while the margins highlight distinct variances. Because both sets of text are from the same field, the majority of the language doesn't vary. We have a lot of crossings. Another example will show how two texts from various fields look on common COCA background. This figure differs in that there are practically no areas of intersection. Since the prior work, we have been able to greatly improve the user experience. Even with a more advanced embedding model, training a new model from zero on a single machine takes 2 hours for 32,719 unique background words. The table on the slide displays all the temporal characteristics of our technique on a single Google Colab system with a single CPU. The difficult part was obtaining suitable hyperparameters and formulating suggestions for other background datasets. We were able to determine the optimum set of parameters in terms of word uniformity and cluster quality due to a comprehensive research. Finally, the goal of this research was to determine the optimum approach for showing text data on a plane that captures commonalities and clusters while without overwhelming the user's perspective. We also focused on the development of software which might be a useful tool for those who don't have programming skills. Based on the results provided, we are convinced that our tool will be helpful for researchers working with textual data. That's all from my side. Thank you very much for your attention.
Thank you, Dinar. Any questions from the online? Maybe some offline questions? No? No? Basically, I have a question. As you showed from the slides, I think one of the last slides, there were some numbers about the time you spent for training, for preparing the low-dimensional representations, and there was one number which is approximately 30 minutes. Can you comment on possible ways of reducing this number? Because like 30 minutes sounds like a pretty big number for a typical user. Yeah, if you want to take the potential user of your application, what can be done to make this number significantly less?
Yeah, thank you for the question. Well, I think it's more about optimization, like using different methods for preprocessing data or another embedding models, maybe, which are lighter. But the time which algorithm, the SOM takes for computation, I think we cannot reduce by ourselves. Only the preprocessing steps might be affected.
I wanted to just to know that for now, as I understand, you use some pre-trained embedding models, and these models they occupy some memory. And what about pre-trained sets which are already like trained some models? Do they take comparable amount of memory? Are they significantly bigger? Are they less? So can they be distributed together with the embedding models?
Yeah, sure. Like in our GitHub repository, we already have some pre-trained sets which can be used like straight from the repository. They are taking not much space actually.
Okay, thank you very much. Any other questions, colleagues? If no more questions, Dinar, thank you very much for your presentation. It was a interesting twist in the robotics session. And I think that we have the last presenter for today, and this is Alexandr, right? He's offline, so please prepare.
Dinar, can you please unshare your screen?
Yep, sorry.
Thank you.
Hello everyone. Today I will talk about analysis of mixed reality cross-device localization algorithms based on point cloud registration. Nowadays, mixed reality devices are developing very fast and can be used for solving different tasks. Usually, to solve any task, people need to work in a group and interact with each other. Therefore, to work together, they need a collaborative localization system that allows to interact in single space. Also, collaborative localization system can allow interact with drones and robots. How can we imagine the target problem? For collaborative localization, we need to find a transformation between two local coordinate systems of mixed reality devices. At the moment, N-course-based solutions are used to solve this problem, but this solution has the following disadvantages. At first, they are very expensive. This rule depends on illumination, such as use visual features, and they don't always provide stable results. What we have, each mixed reality device built his own special map consisting from meshes, and each special map is set its own local coordinate system of the device. And we need to find a transformation between these local coordinate systems. How we can find this unknown transformation? We can use point cloud registration solution. It is possible, such as special map of mixed reality devices can be represented as point cloud. For better imagination on this slide, the process is shown on the example well-known rabbit model. Point cloud registration solution allows to calculate unknown transformation and hence localize the devices. Visually, the right solution of point cloud registration can be represented as point cloud matching, as shown on this slide. So our general goal became to develop a plan capable of solving the problem of indoor mixed reality cross-device global localization. The task were the next. At first, efficiency comparison of chosen global registration methods on real point clouds of indoor environments to detect respective methods are suitable for solving mixed reality cross-device localization problem. The second, more detailed analysis of the effectiveness for more perspective registration method for different parameters and method modifications. And the final detection of the weak points of the approaches and obtaining results for fine-tuning of approach for real applications. In our work, we investigated and used the following registration methods: ICP, OCP, Bayesian ICP, fast global registration, and teaser++. Each registration method try to solve the following general problem. We have dataset A and dataset B. I mean point cloud A and point cloud B. And we want our task to estimate transformation between 2 point clouds expressed as rotation and translation that allows to minimize the following arrow function. The next slide presents key features of point cloud registration methods. The main moments that you can remember from this slide, I think the registration methods divide in two categories, ICP-based methods and feature correspondences-based methods. ICP-based methods solve registration problem iteratively, but at the same time, feature-based methods solve the problem for one pass. It's more faster and give +1 for feature-based methods. Also important to say that ICP method registration is not, it doesn't provide a global solution, but it's accurate for small bias between point clouds. We will more concentrate about fast global registration and Teaser plus registration methods, and it is open to know more about their main components. They have feature the same submodels, feature extractor, and advanced matching. Transformation estimator is different for these algorithms. Teaser has interest submodel, maximal QQ inlier selection based on graphs that allows to reduce a lot, significant amount bad correspondences. Fast global registration in Teaser has as feature extractor fast point feature histogram as default. To calculate feature points. Feature points is a descriptor that allows to describe local geometry in the point cloud. We tested the novel features descriptor, which is shown in the right side of the slide, weight, height, image descriptor. Key facts about descriptors you can see on this slide. The main to say here that this descriptor is based on different conceptions, and weight, height, image descriptor has more advantages than fast point feature histogram. Also important to say about advanced matching, such as you will see in the next slides, that this case submodel that limits point cloud registration methods, fast global registration, and Teaser++. This submodel consists from 3 steps: nearest search to build correspondences in multi-dimensional feature space, cross-validation, and tuple checking to prune correspondences. We use 2 modes of this submodel, mode on and mode off. Mode on, it does mean all 3 steps are used in this submodel, and mode off, only first step is used. To analyze efficiency point cloud registration methods, we created 2 real datasets, dataset A and dataset B. Dataset A is open source dataset collected from RGBD camera. It contains different areas such as living room, office room, corridors, point clouds, and dataset B is dataset collected by us with mixed reality devices, Microsoft HoloLens first generation and Microsoft HoloLens second generation. This dataset contains sparse point clouds of 4 areas, 3 different rooms, and corridor. Also, we created synthetic dataset from dataset B. For this, we copied different size parts from each large point cloud in dataset B and set ground truth transformation for each pair point cloud. The basic idea of synthetic dataset is able to estimate the accuracy of point cloud registration. The methodology is the following. At first, we evaluated the registration effectiveness of algorithms on real dataset A and B. Second, we estimate the registration effectiveness for the algorithm's fast global registration in teaser plus pass, depending on different radius and features on synthetic dataset. And finally, we evaluated the registration effectiveness dependent on different parameters for a hybrid approach. And let's go to results. Here you can see efficiency of registration algorithms on a real dataset, dataset A and dataset B. If you look at rows Go OCP and Bayesian OCP, you will see that these algorithms spend a lot of time and give very low registration success. If you look at column alignment success, you will see that for fast global registration in teaser plus in dataset B, we have low alignment success. It says that dataset B is more complex dataset for registration than dataset A. I will remember that dataset is open source dataset, and dataset B is created by mixed reality devices. Also important to see here that when we use advanced matching with turn off, we can see that for VHI feature descriptor, we obtain 100% registration success. The next slide shows accuracy and runtime analysis for fast global registration for different feature descriptors. The key moment here that feature descriptor VHI give the more accurate registration, and by using this feature descriptors, we can do registration more faster. The same trend for teaser plus. And the next slide shows results on synthetic datasets for different feature radius, different threshold ICP, and different feature descriptors. These results can be used, can be important for engineers, for example, to fine-tuning their real application by using this approach. Same for teaser plus, and what we noticed results shows that advanced matching is a weakness submodel of fast global registration in teaser plus. Why it's happened so? It is because advanced matching has the following limitations. F1 algorithm near search in advanced matching is used 2 times to find more exact correspondences. Cross validation is used to compensate small precision of F1 algorithm, and tuple checking is constrained with random result output. And solution here can be to replace advanced matching algorithm by nearest search algorithm with high precision. On this slide, you can see a simple demonstration of collaborative localization implementation for mixed reality devices in case hoops manipulation. Here, 2 users stand opposite each other and manipulate sequentially by hoop. This slide shows the total results, and our future work is to extend the approach for collaborative localization of multi-robot system and multi-mixed reality device in one space. And also we will investigate the methods for global registration of mixed reality devices in large pre-built and labeled maps. That's all. Thank you for attention.
Thank you very much for your presentation. Any questions online? Maybe offline. If you don't mind, can you open the slide with the time comparison, where you have dataset A, dataset B, with the numbers? Just I wanted I was wondering, so I'm not into the topic, but what I see in the table, like for both methods, the teaser plus method with advanced matching off is the best one, because like it's the only method which can do 100% alignment success. Yeah.
Yes.
Okay. So and from that table, I see that in the dataset A and the dataset B, the difference between this advanced matching feature on and off is completely different. So for the first, for dataset A, you have 5 times speed up, whereas for dataset B, you have only 1.5 times speed up. What can be the reason for this?
It happens because dataset A consists from dense point clouds, and dataset B consists from sparse point clouds. When we have dense point clouds, we have more points and we have more population for this. And what's your question about runtime or?
Yeah, so I'm wondering why the feature is not scaling. So you have the harder data set. So the dense one is dense, one is sparse. But the feature.
I mean, when I said about hard that that's a bit is harder. That said, it means that we have less registration success. You can see
it's interesting that in with scaling, so the time in the first case in dataset A is significantly bigger than in dataset B. So for single run, but the feature improves time significantly in the first case and insignificantly in the second case. Now you see that for the WHI16, you have 3 times speed up in the dataset A, and only 2 times speed up in dataset B. Okay?
Of course, because it's another question when we have it can be not be linear proportional increasing of runtime. It depends on amount of points for these features. For example, when we have small amounts of points in this region, we have a linear, for example, increasing of runtime with this amount of points. Then we have a lot of big points. In this region, we have, for example, non-linear dependencies on amount of points for runtime.
So it means that this results not on the algorithm scalability, it's more the evidence of different the local density of the data.
Yes.
Okay.
But in real scenarios, we have dense of point clouds in the range, some range. So for us, it's enough to investigate in this range, and if we get success results in this region, for us, it's enough to solve problem for real application.
And one question is from my professional area, basically. So as I'm into information retrieval, definitely what I see that these features, the 16-dimensional and 36-dimensional, they definitely don't fit to k-dimensional trees. So like even on the website of scikit-learn, they say that if you have 15 dimensions, it's better not to use k-trees. Because the accuracy drops or
important that we reduce dimensionality, we lost information, lost descriptiveness of these features.
What's the final dimension?
What we prepare to use, you mean? What's your question?
The question is that, so I see that there is a number, you said that there are descriptors which are 16-dimensional and 36-dimensional. And you use this advanced matching algorithm, which basically searches in the index, in the k-dimensional tree. You use the Flan algorithm, right?
Yes.
Okay, yeah, so based on the recommendations of the researchers who study these algorithms, they say that the higher the dimension, lowers the quality of k-dimensional tree. So that's basically the curse of dimensionality. So what do you plan to use instead of one in your studies?
We already use another algorithm created by researchers from Russia. This algorithm allows to find correspondences with precision 90%.
What's the algorithm?
I don't remember. Based on graphs.
Okay, it's HNSW.
Navigation graphs.
HNSW, NMSD. So most probably this is.
Navigation graphs more work.
Yeah. So basically, it's a good choice. Okay, thank you very much for your answers. Any other questions? No? Then let me thank you again for your presentation. And we are closing the session in artificial intelligence and computer vision right now. Let's have a small break and let's meet again in 20 minutes, right? In 20 minutes. Thank you.